So it's going to be an MIMD interpreter for genetic programming, and the authors are Vinícius de Melo, Álvaro Fazenda, Léo Françoso, Piccol Sotto, and Giovanni Iacca.
Hi everyone, I'm Leo. I've done this work together with Vinícius and Álvaro and Giovanni, and we have proposed a MIMD interpreter for genetic programming. So here we have a summary. I'm going to give an introduction, show some related work, introduce the MIMD interpreter I have proposed, and show some results comparing it to a SIMD interpreter, and the conclusions. Okay, so the main bottleneck for standard GP is the fitness evaluation. So we have to evaluate each individual on each dataset case, and depending on the population size and also on the number of fitness cases, it may take a lot of time. So there are many proposed solutions that try to speed up this process. Most of them rely on the parallel evaluation of individuals, so using, for example, multi-core or GPUs or distributed evaluation. And there's also the use of SIMD operations, which are single instruction on multiple data. So we operate an instruction on more than one data at once. So in our proposed approach, we include MIMD instructions in the GP interpreter. So we execute multiple instructions on multiple data, and we can operate up to 4 float operations in parallel. So some related work. Most applications rely on some GPU-based implementations of GP. Most of them use CUDA or OpenCL. So here we have some examples. There's also a framework called Keru GP that uses TensorFlow from Python, and they all run the evaluation process of GP on GPUs. There are also some data parallel approaches that use some data parallel features from GPUs to run the evaluation process of GP. Also, Langdon and Bansav have proposed a postfix stack-based interpreter running on GPUs, and Chiti has used this interpreter but on CPUs, and also with SIMD operators, cache optimization, and doubled operators. So this last approach is the most similar to what we have proposed, but we use also more MIMD operators instead of only doubled operators. So now we move to the proposed interpreter. So we use a postfix notation and a stack. So for example, in a standard operation, for example for A plus B, we would do A plus B, assign it to a temporary array, and return it. So using the stack, we actually have we push A onto the stack, then we push B onto the stack, and we sum the top -1 plus top and decrease the top by 1. So we have in-place operations and do not need to assign the result to temporary variables. So the stack must have first dimension, that is the maximum tree depth. The first dimension of the stack is the maximum tree depth, and the second dimension is the number of fitness cases. So each position in the stack is an array with all fitness cases. So in one iteration we can evaluate all fitness cases, and then we can reduce memory operations, and also we can enable SIMD instructions. And what we propose to this interpreter are MIMD instructions. So we can operate multiple operations in a single line, and thus we have less iterations on the data, and we also have less push and pop operations on the stack, and we allow some compiler features like fused multiply add and instruction level parallelism. So the main instructions we propose here are here on the table. So there is an identifier for each of them. For example, from A to X, and we use instructions that operate on 3 arguments or on 4 arguments. So for example, here we have A, B plus C plus, which is in the traditional form A plus B and then A plus C, and in the proposed form it is A plus B plus C all in one iteration. So instead of having 2 iterations, we have only 1. And for example, here we have A plus B, C plus D, and then plus. In the traditional form we have 3 iterations, and in the proposed form we have only 1 iteration. And here we test only 8 4 arguments operations, but we can also use more, all possible combinations. So here's an example of a proposed MIMD instruction. So we have A, B, and C, which are the top and the first 3 arrays on the stack. Then we iterate on all fitness cases and do A times B plus C. So we perform here 2 operators in 1 iteration. And we also need to use some pragmas in order to enable auto-vectorization and some compilation flags in order to optimize the compilation, and also you need to use this AVX2 in order to use auto-vectorization and AVX2 instructions. So we use SIMD and MIMD features of the processor. So if we use another processor, or if you want to use the approach on GPUs, you would have to adapt these flags or these optimizations in the codes, but it's possible to do so. So we have tested our approach. In order to do that, we have used synthetic datasets with 10 variables from -1 to 1, and we have generated a number of postfix expressions and evaluated it in a single generation. So we do not execute a GP run. We only run a single generation and compare it with the SIMD interpreter. So we generate individuals already in the postfix representation, and because of that we need to use a lower depth for the MIMD interpreter, because some operations in the MIMD interpreter are composed of up to 3 operators, up to 3 basic operators of the SIMD interpreter. So first we have analyzed the MIMD instructions individually. So we have run 1000 independent runs of each operator for a dataset of 1 million cases. So for example, here we have tested instruction A in the SIMD interpreter, in the MIMD interpreter, and we measure the speedup. So for example, instruction A, here is A plus B plus C. In the SIMD interpreter, we'll have to perform 2 iterations, and in the MIMD interpreter we perform only 1 iteration. So we measure here the speedup of the MIMD interpreter, which is here. So we have here a speedup of 16%. This speedup is similar for all 3 argument operators, and for the 4 argument operators it is a bit higher, 25%, and on average we have a speedup of 19, or between 19 and 20% when using the proposed MIMD operators. So here we compare the SIMD interpreter in black with the MIMD interpreter in blue. We execute 30 runs and use a Wilcoxon test in order to identify if the difference between the interpreters is significant or not. And all differences were significant here. So here in the x-axis we have the dataset size from 100 to 1 million cases. Here we have the population size from 100 to 10,000 individuals. And in the z-axis we have the number of GP operations per second in billions. So what we see is that the pattern for both interpreters is similar, so both of them grow in number of GP operations and then decrease. There's also a difference between the 2 interpreters, which is statistically significant for all dataset sizes. And well, the number of individuals did not impact the performance. And what we can see here is that we have a number of GP ops that increases when we increase the dataset size, because we have more data to work on and then we can perform more operations. But when we use 5,000 fitness cases, then the performance of the interpreters decrease, and it continues decreasing as we increase the dataset size. So we have also analyzed what happens in the cache memory. So here we can see the data for the 3 levels of cache, R1, L1, L2 and L3, both for the MIMD and the SIMD interpreters. And what we see is that beginning with 5,000 fitness cases, the cache miss rate for L1 increases, and we see that with 5,000 cases here, the number of GP operations per second decreases. We also see that with 50,000 cases, the cache misses rate of L2 increases, and there is a further decrease in the performance. And with 1 million cases, the L3 cache miss rate begins to increase, and there is a further decrease in performance. So what happens here is that as we use larger datasets, we need more swap operations, and then the impact of using SIMD or MIMD operators decrease. That's the explanation, and that's also a limitation of the proposed approach. So now we move to the conclusions. We could obtain a speedup of 20%, an average speedup of 20% when we evaluate the MIMD operators individually. And we also, the MIMD interpreter was also able to outperform the SIMD interpreter for all dataset sizes. And there is a correlation between the performance of both interpreters and the dataset size, and the reason for that is the increase in the cache miss rates, and also the difference between the MIMD and the SIMD interpreters is affected by the dataset size. And for future work, we intend to investigate better the effect of these swap operations on the performance of the MIMD interpreter, so we can maybe improve it. We also want to test the interpreter on complete GPU runs, where we have to convert the tree to the postfix notation and run for more generations. And it's also possible to apply this approach on multi-core CPUs or GPUs, so we could also consider that. Okay, so here we have some references, and that's it. Thanks for watching.